Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aimrasul bin Zulkifli, metric number 1240917. Today, I will be presenting my project titled Modeling Newton's Laws of Cooling using WOLFRAM Mathematica. To begin, differential equations offer a fundamental mathematical foundation for simulating dynamic real-world systems. They capture a continuous rate of change that conventional static algebra fails to represent. While manually deriving analytical solution for this behavior can be time-consuming and prone to human calculation mistake, technical computing systems provide an effective high-precision alternative. This computational method works exceptionally well with WOLFRAM Mathematica, which smoothly integrates two-dimensional vector visualization. For this physical scenario, a fresh cup of hot coffee is served at initial temperature of 90 degrees Celsius and left to cool in a dining room regulated at a constant 20 degrees Celsius at temperature. The objective of this study are twofold. First, to formulate Newton's law of cooling using a computational approach, and second, to analyze the thermal decay characteristic of a 60-minute period. We're moving on to the methodology. According to Newton's rule of cooling, the temperature differential between an item and its surrounding determines how quickly heat is exchanged between them. Mathematically, this is expressed as dt over dt equal negative k times the quantity T minus TA, where T of T is the temperature of the coffee at any given time T. TA is the constant ambient room temperature of 20 degrees Celsius, and K is the thermal cooling or heat loss constant, which is 0.05. The initial condition is that at T equals 0, the coffee is cooled at 90 degrees Celsius. Now, let's look at the core highlight of this presentation. The computational solution executed directly within WOLFRAM Mathematica. To evaluate this initial value problem without manual calculus overhead, we write a highly efficient two-line script. As seen on screen, we first use the dissolve command to combine our differential equation with our initial condition, adding the simplify operator to clean up the output. Right below it, we call the standard plot command. By passing our solved solution through a replacement operator, Mathematica automatically generates a beautiful vector graph map over a 16-minute domain, complete with custom X label, plot styling, and grid line. When Mathematica evaluates the system analytically, it produces the exact cooling model equation T equal to 20 times plus 70 times exponential to the power of negative 0.05 T. Looking at our graph from 0 to 20 minutes, the coffee temperature dropped quickly due to the significant temperature differential between the hot coffee at 90 degrees Celsius and the surrounding room at 20 degrees Celsius. This leads to a high initial cooling rate. As the coffee cools down, this temperature gap gets smaller, meaning the cooling rate decreases exponentially. Ultimately, the coffee finds thermal equilibrium with its surrounding environment, which is clearly indicated by the curved slow approach to an asymptote at 20 degrees. So in conclusion, this study successfully combined computational calculus with a classical thermodynamic theory to examine heat transmission in a liquid system. By utilizing WOLFRAM Mathematica, this model effectively minimizes human error and significantly lowers computational complexity. The finding properly depict actual real-world cooling behavior through an exponential decline curve that perfectly approaches our ambient room threshold. Overall, this computational method offers a highly scalable and effective way to expand and visualize complex thermodynamic models in the future.